Welcome back students to the part 4 from the chapter Moving Charges and Magnetism. In this module, we will be discussing about torque on a current loop and magnetic dipole. So let us consider a rectangular loop such that it carries a current of magnitude I. If we place this loop in a magnetic field, it experiences a torque but no net force, which is similar to what an electric dipole experiences in a uniform electric field. Now let us consider the case when the plane of the loop is not along the direction of magnetic field. The angle between the field and the normal to the coil be given by theta. We can see that the forces on the two arms will always act opposite to each other and will be equal in magnitude. Since these forces are the equal, opposite and collinear at all points, they cancel out each other's effect and result in zero force or torque. The forces on the arms AB and CD are given by F1 and F2. These forces are equal in magnitude and opposite in direction. So from this figure, the rectangular loop is placed between the poles of a magnet so that a region of uniform magnetic field is present in the area of the loop. Let B be the length of the loop and A be its breadth. A current I is passing through the loop. The ends of the loop are connected to two split rings which are connected to a battery by means of carbon brushes. Let ABCD be the rectangular loop under consideration, and the axis of rotation of the loop is as shown in the figure. Sides BC and AD will not contribute to the torque as their forces are collinear, but the sides AB and CD will contribute to the torque since their forces are equal and opposite. So the direction of forces are as shown in the figure. They will be equal in magnitude but opposite in direction. So by applying the equation for torque as force into perpendicular distance from the axis of rotation, we get tau is equivalent to F into A by 2 plus F into A by 2 due to the sides AB and CD. This is the case when the plane of the loop is along the direction of magnetic field, or the normal to the plane is perpendicular to the direction of magnetic field. So the total torque is given by F into A. Instead of force, we can substitute I into small a into small b into capital B, where F is equivalent to I into dl cross B. Here dl is the length B and magnetic field is B. Since small a into small b is the area of the loop, torque can be written as I into A into B. This is the maximum possible torque. In general, if the normal to the plane of the coil makes an angle theta with the direction of magnetic field, torque is given by I into A cross B. area is to be treated as a vector and direction of area is always normal to its plane. So the torque in vector form is given by tau is equivalent to Ni into A cross B, where N is the number of loops of the rectangular coil. I is the current passing through the coil, A is the area of the coil, and B is the magnetic field. Here, the term N into I into A can be replaced by mu or small letter m, where m is called the magnetic dipole moment. And the direction of magnetic dipole moment is in the direction of A, that is area of the loop. Hope you have understood about the torque experienced by a rectangular coil placed in a region of magnetic field and the concept of magnetic dipole moment. Thank you, dear students.